Okay, so I uploaded the recorded lecture last Thursday, and I asked all of you to take the online course before attending today's class. If you haven't yet, you will lose your attendance point. But you still can take online course until the midterm to get attendance point as a lateness. So if you haven't taken the class yet, please attend to the recorded online class. Okay, so as usual, I'm gonna do a brief review for the contents and move on to the contents we're gonna study. So this chapter is about learning acid and base, which is very important concept in general chemistry too. So there are various definition, and the most important concept in this chapter is a Bronsted acid and Bronsted base. So Bronsted acid, proton donor. So every time you have some substances as an acid, you can write down this is acid, and this is a conjugate base. And for any substances that can be bases, you also can write down base. The reason why I keep writing down these very basic equations today is that what you're gonna learn later today's lecture is very important to remember these very easy basic equations. So after learning the concept of Bronsted acid and base, you learn some concept about the ionization ion product constants of water, Kw, where the concentration of H plus times concentration of OH minus is a constant, always to be 10 to the minus 14 at 25 Celsius degree. This is also very important relationship you must remember. And you learn how to define pH based on the concentration of H plus, and the same way to define pOH by the concentration of OH minus. And you try to solve various problems to convert concentration of H plus or OH minus into pH or pOH. And you learn the concept of strong acid, weak acid, and strong base, weak base. So every concept and every problems about strong acid and strong base are very simple, because you can just always assume that 100% of acid and base directly generate H plus and OH minus. But the problem that becomes more difficult is about weak acid and weak base, because weak acid and weak base, the only partial amount of them are dissociated into H plus and conjugate base, which can be quantitatively expressed in chemical equilibrium concept using equilibrium constant Ka. So if you have this weak acid written by Ha, this is the basic equation regarding acid, and you can always define the acid ionization constant Ka based on this equation. It's really important to remember. So depending on the value, the size of Ka, you can tell whether how weak or how strong the weak acids are. So higher the Ka, that means your acid strength is higher, and you will get a higher concentration of pH plus, and you will get lower pH. And the one thing that I want to mention here is that in this table, you have a very many lists of weak acid and strong acid and weak acids. So this is the more strong strong and this is weaker. So this is the strong acid. So if you write down some equation based on this strong acid, it can be plus H2O H3O plus ClO4 minus, right? And you know this is the base and this is the acid and this is the conjugate base. And if your acid is very, very strong, that means chemical equilibrium in this equation lie far to the right, right? Which means that the conjugate base, the strength of conjugate base is exactly the opposite, with opposite to the strength of acid. Which means that if you take this as a one kind of a base, you also can write down new equation from the perspective of this conjugate base, which can be right. Right, because this is a base, you also can write down this equation. So here, this is a base. This is a conjugate acid. So because the pair acid for this base is very, very strong, which means that the strength of this base is very, very weak. So the Kb here would be very, very low. So if you take another example in another side, which is, for example, this one, acetic acid, you can write down an equation from the perspective of this acetic acid. Because this acetic acid is a weak acid, from the perspective of chemical equilibrium, this equilibrium lies to the left, right? It has a tendency to lies to the left, which means that this is acid, this is a base, conjugate base. So because this COOH, acetic acid, is a weak acid, so comparatively, 상대적으로, this base is strong, right? Which means that if you write down new chemical equation from the perspective of this conjugate base, it can be right? So it means that if you have the acetic acid anion, because the strength of this base is quite high, so you will have this. You can expect this chemical reaction to happen. And this is a very important concept. So I will I will teach you later today. So you always know how to write down this equation from the perspective of acid and also from the perspective of conjugate base. So you can define Ka for this equation and you can define Kb for this equation because it's an acid base. Okay. And you try to solve any problems regarding strong acid or strong base, HCl or barium hydroxide. It's always very easy. You don't need to solve any equation. But when you move on to the weak acid, you have to calculate, you have to do some calculation because they only the partial amount of HA will be dissociated into this H plus and conjugate base with equilibrium constant Ka defined like this. So this is the Ka value for various weak acid. As I mentioned before, there are only several types of strong acid, 황산, 염산, 질산 등등. But other than that, most of acid are actually weak acid, which means so there are much more types of weak acid than the types of strong acid. So you just remember the list of strong acid, and if the unknown acid is not in the list, then you can assume that that acid is a weak acid. And for every weak acid, you always will be provided in exam with the Ka value like this. Okay, and with Ka value, you can also always define the Kb value, which is the strength of conjugate base. So you can tell that the higher the Ka, which means the stronger the weak acid, then the smaller the Kb, which means the weaker the conjugate base, right? So 10 to the minus 4, 10 to the minus 11, and the 10 to the minus 10, and 10 to the minus 5. So their relative strength of conjugate acid and conjugate base are in opposite. And there are various ways to describe the strength of acid. So you can describe the strength based on Ka value. If Ka is high, the acid is more stronger. And you also can describe from the position of chemical equilibrium from this equation. And also you can describe based on the concentration of H plus versus the initial amount of HA, initial amount of acid. And also you can describe the strength of acid based on the strength of conjugate base. So this statement is what exactly I just explained in previous page based on So these two statements tells you about the position of this position of equilibrium in this chemical equation where the conjugate base acting as a base here. Okay, so this is the page where you want to try to solve some calculation problem about weak acid. For example, HF. So HF is a deionized following this equation with the Ka value here. So you can do the same thing that you did for when you solve the chemical equilibrium problem in previous chapter. So from the initial value, you can expect the HF will be decreased and the H plus and F minus will increase in the same stoichiometric ratio. So you can write down the equilibrium as with unknown variable x, and you can make some equation to calculate the Ka, and you will get this quadratic equation. So because the Ka value in most cases of weak acids are very, very small, right? If you go back to the table here, most weak acid has a very low, very small Ka, which means that the X here, the portion of ionized species will be very, very small. So in many cases, you just need to, you just can do some approximation where this can be, so you can do very approximation in most cases, and if you do this approximation, it becomes really easy to solve this equation. And every time you solve x based on this approximation, every time you do that, you have to confirm whether the approximation is valid or not by checking whether x is larger than 5% or smaller than 5%. So in this case, x is smaller than 5%. So the approximation is valid in this case. So this is another example where you try to solve the pH of solutions with weak acids using these equations. And in this case, in this specific case, you see that the x is larger than 13%, which means the approximation is not valid. If that's the case, there's no way other than solving this quadratic formulas by quadratic formula, 근해 공식. Okay. Okay. So in the same way you define the Ka, the strength of acid, you can do the same thing to define the Kb, strength of weak base. So this is a base plus H2O and conjugate acid plus OH minus. So in this equation, you can define the Kb like this. So Kb is called the base ionization constant. So the higher the Kb, the strength of a weak base is stronger, is higher. So in the, also for many weak bases, you can define Kb. And also, if you have a weak base, you always have a conjugate acid, and you also can define the Ka of conjugate acids. And you can do the same thing in case of conjugate base, in case of a weak base. So here the approximation is valid because this is less than 5%. And yeah, and this is the first page that we are going to study today. So you define, this is the, let's take an example of acetic acid, which is one kind of a weak acid. So this is a weak acid, and you can write down the basic equation on acid, right? And you can define Ka. And here, if this is a weak acid, you can define conjugate base, which is this. And you can write down new equation from perspective of this conjugate base, which can be this, right? This is exactly the same equation that I wrote down when I was reviewing the contents. So from this base perspective, you also can define the Kb, the base ionization constant, in this equation. So, and then here, if you multiply Ka, the acid strength of weak acid, and the Kb, the base strength of conjugate base, you will have this relationship and this relationship. So what this tells us is that the Ka and the Kb of conjugate base is always Kw. Always have this relationship. So this is why that you have this relationship in page 24, where the strength of acid and strength of their conjugate base are exactly opposite, which is that their product is always Kw, the constant. Okay. So so now we gonna study some special types of acid that can donate more than 2 protons. So if some substances can donate proton 2 times, we call them diprotic acids. And if some substances can donate 3 protons, we call them triprotic acids. So I would say in Korean, 2양성자산, 3양성자산. So let's take an example of this H2CO3, which generated from the CO2 into dissolved in water. So the first ionization reaction is this, and you can define Ka1 based on this equation. And here, this is an acid, and this is a conjugate base. But this conjugate base also can act as an acid in this case because it still has 1 proton to donate. So this is the second ionization reactions where you can also define the Ka2 for this second step. Okay. Here is our acid. This is a conjugate base. So this is actual examples of diprotic or triprotic acids. And what you can see is that the size of Ka is always higher for the earlier step. So for example, this H2SO4, the initial the Ka for the first deprotonation reaction is very large, but for the second deprotonation reaction is this. And for the other acid, for example, oxalic acid, the Ka for the first step is this, and the second step has a Ka value of this, which is much lower than the first one. And the same thing for all the other diprotic or triprotic acid. So you can see the Ka becomes smaller for the following deprotonation steps. And also in this case, the Ka value, Kb, the product of Ka and Kb always become Kw, always. Yeah, in every cases. Okay. So this is the example where you are required to calculate some solution pH of some solutions containing diprotic acid, oxalic acid in this case. And to solve this problem, you have to approach step by step. So you have to approach how much this oxalic acid will be dissociated into first step, and then you move on to the second step where you repeat the same process. So for example, you want to, the final thing that you need to calculate is calculate the concentration of all the species present at equilibrium. What it means by all the species is that if you dissolve this oxalic acid into solutions, you will have H plus, and you also have He2CO4 minus, and you also have C2O4 2 minus, and you also have OH minus and H2O. So these are all the species that you would have if you dissolve this oxalic acid, and you want to calculate the concentration of every single components here. So you do step by step. So the first thing you do is to just calculate following the same process for the first step, ionization, where you have initial concentration, and you have a change, and you will have the final equilibrium expressed as some variable with unknown x. And for this oxalic acid, you know the Ka value for first step and the Ka value for the second step. And for this first step, you need to use the Ka value for the first step So this is the Ka1 value, and you make some equation with unknown variable x, and you want to do approximation because it's always a easier way, and you calculate x, and then you found that the x is much larger than 5%, which means the approximation is not valid. So the approximation doesn't work here. So you need to solve this quadratic equation, 2차 방정식. And here, if you solve this 2차 방정식, you will get the x equals 0.5 mole. So after first protonation is finished, you will have this amount of H plus in solution, and this amount of HC2O4 minus, and this amount of remaining unionized initial weak acid, right? And then you move on to the second ionization step, where you do the same thing with another unknown variable y, and you follow the same step, and you have a different Ka value, Ka2 value in the table, and you do the same thing, and in this case the approximation is valid because the y value is the less than 5%, so you can calculate y, right? So you can calculate all the final concentration of all the species. And here, some students would have some questions, right? We have this diprotic acid. So we have in solution, these two reactions is happening at the same time, right? And they try to approach the chemical equilibrium based on their relative chemical equilibrium constants, right? And the first thing we did to solve this problem is to calculate the equilibrium for these first equations, and then we fix the concentration from this first equilibrium, and then we solve the equilibrium for the second reactions. It might be doesn't make sense, because once you move the equilibrium position for this second step, what you do is you change the concentration of this. This is the another reaction product for these reactions, and that the change of this concentration will also have the equilibrium. It also shifts the equilibrium for these first reactions. So it doesn't make sense to solve the first equation and fix all the calculation value and then move on to the second reactions. That's right. They are interconnected, so the equilibrium position moves at the same time. But the reason is that they have so much different Ka value. So the Ka1 is much larger than Ka2. So even though from these second reactions, even though you have a little bit slightly decreased the concentration of HC2O4 minus, that's very small. So you can just assume that the concentration of this HC2O4 minus is very small. So the influence of this concentration change to the equilibrium position for the first reaction is not that huge, right? So let's say so for example, for the second chemical equilibrium, this is y, right? This is y, the unknown variable y. Then if you generate this amount of C2O4 2 minus, which means that the same amount of H2 C2O4 minus will decrease, right? So to be more precise, then the concentration of this H2O4 minus would be minus, right? But this value is very, very small, less than 1%. So you just can write down answer is just this value. Okay. So if I, because this concept is a little bit really important to understand, let me explain in Korean one more time. So 원래는 요 두 반응이 서로 연결되어 있기 때문에 첫 번째 반응을 풀고 나서 그 반응에서 구한 농도가 픽스되어 있다고 가정하고 두 번째를 풀면은 이게 지금 농도가 바뀌면서 첫 번째 반응의 평형을 다시 바꿀 거기 때문에 엄밀히 말하면 그게 말이 안 되지만 이 두 번째 반응으로 인해 변동되는 농도의 비율 자체가 극히 적기 때문에 첫 번째 평형에는 거의 영향을 안 줄 것이고, 따라서 문제를 일반화 수준에서는 문제를 푸는 과정 중에는 이렇게 첫 번째 그 먼저 일어나는 반응은 그 다음 일어나는 반응 때문에 영향받지 않는다라고 가정을 하고 풀어도 문제가 없습니다. 따라서 뭐 얼핏 보면은 이렇게 이양성자산이나 뭐 다양 3개의 프로톤을 내놓을 수 있는 반응들의 경우에는 문제 푸는 게 되게 복잡해 보이지만 걔네들의 Ka 값이 서로 큰 차이가 있기 때문에 그냥 위에 거부터 차근차근 풀면은 그냥 이렇게 된다고 알고 계시면 될 것 같습니다. Okay. Let's move on to the little bit more qualitative understanding on the strength of acid. So far we approached quantitatively, 정량적으로, by using Ka. But from this page, let's try to understand the relative strength of acid in qualitative way, 정성적으로. Okay. Let's say that you have this compound HX, which can be potentially acid by generating H plus based on this equation. And from the perspective of electron cloud, electron density, in many cases, this X atom here, X atom, has a slightly more electron density, so you can write down this a slight negative, and also then at the same time the proton H plus has a slightly less electron density, so it's a slightly positive. And the extent of this electron density asymmetry based on the electronegativity of these X atoms. So if this X atom has a higher electronegativity, then this the asymmetry become larger, and if the X has a lower electronegativity, then the asymmetry becomes smaller. So based on this relationship, and if this becomes more polar, that means they have a more if for example F has a higher electronegativity than this I minus, so the electron density will be more polar like this, then the bond between here becomes more stronger, becomes a little bit ionic. So if you compare these four acid, these four hydrohalic acid, halic means a halide, hydrohalic acid, HF, HCl, HBr, HI, based on their relative electronegativity, of these halide anions, you can calculate the bond enthalpy of these 4 different acids. And as I mentioned in chapter 12, the enthalpy is the expression of the bond strength between these 2 atoms. So the higher the enthalpy, the stronger the bond. So the HF has the strongest bond strength, and the HI has a weakest bond strength. So if the bond strength is stronger, which means that it's relatively more difficult to detach the proton atoms, right? So that means these chemical reactions, deprotonation reactions, is for HF, this will tend to be the chemical equilibrium tend to lie a little bit left, and for HI, which has the weakest bond enthalpy, this equation tend to lie right. Okay, so that's why the HF is a weak acid, but other acid, HCl, 염산, or HBr, HI, they are all strong acid. And also you can understand the relative acid strength of oxo acids. So oxo acid is by definition, oxo acids is the substances that contains hydrogen and oxygen and one other element Z, random element Z, at the central position. So for example, these are the list of oxo acids, examples of oxo acids. And also you can qualitatively understand the relative strength of these oxo acids. For example, let's compare the relative strength of these oxo acids. Right? In this case, Cl and Br are the only differences, and other than that, their structures are identical. So let's compare the relative electronegativity of these two, Cl and Br, brom. And you know that the Cl has a higher electronegativity than Br, which means that the electron density becomes relatively higher around the Cl, which means that here there is much less electron density between O and H, which means that the H is easier to be detached. So if you compare these two, the oxo acid with Cl and oxo acid with Br, then you will have this relative acid strength, because the H proton from HClO3 is easier to be detached. So the acid strength will be higher for HClO3. So another qualitative comparison that you do between oxo acids are based on the relative oxidation state. For example, let's say that you have these four different oxo acids where Cl has a different number of surrounding attached groups. So the oxidation number for Cl is +1, +3, and +5, and +7 in these cases. And if you have a very high oxidation state around for Cl, that means the electrons are more attracted toward the Cl, which means that electron density between H and O will decrease, which means that H is very easy to be detached. So the higher the oxidation state of Cl is, that means easier the proton is detached, which means the strength of acid is higher. So this this is the relative acid strength between these four different oxo acids. Okay, so if I summarize, in this general oxo acid, when they becomes acid by this proton detached to generate H plus, if the depending on the electronegativity or oxidation state of this Z atom, you can relatively compare the strength of oxo acids. So this is the example where you need to compare the acid strength between various oxo acids. For the first example, is the HClO, HBlO, and HIO. You need to compare the relative strength of these three oxo acids, and you know that from this order, electronegativity is higher. So that means the electron here is much smaller, so H easier to be detached. So the H So the relative strength of acid will be in this order. And another example is H3O plus HNO3 versus HNO2. And in this case, the N here has a little bit higher oxidation state. So this is the 5 plus. For N, this is a 3 plus. And because the nitrogen here, HNO3, has a higher oxidation state, and you can expect the proton here easier to be detached. So the HNO3 is a stronger acid than HNO2. And this is why HNO3 is a famous strong acid, 질산, while HNO2 is a weak acid. So if you go back to these slides where you see the HNO3 nitric acid is a strong acid and HNO2 is a weak acid because of the oxidation state of nitrogen is different in these two cases. Okay. And so far, most of the acid that we studied so far are inorganic acid. And now let's study the one example of organic acid, which is carboxylic acid. So the acid that we previously saw, HCO3, COOH, acetic acid, is a one type of carboxylic acid. So if some organic molecule looks like this, has this structure, then this part, COOH part, this COOH part is called the carboxylic group. And depending on what functional group R is attached to this carboxylic group, then it determines the strength of this carboxylic acid. And then if this carboxylic acid is ionized by this H plus is detached, you will have this anion, carboxylic acid anion. And this carboxylic acid anion has some resonance structure In the same way, the benzene has a resonance structure. So, as I said, this functional group R determines the relative acid strength of this carboxylic acid. So if you compare these two carboxylic acid, where for this one you have a CH3, and for this one you have a CH2Cl. And you know that the Cl minus has a higher electronegativity than H plus. So the electron density around the carboxylic acid, electron density around here will be more attracted toward this functional group in case of CH2Cl, which means that the bond between H plus and OH minus will be more loose here, so H is easier to be detached. So that's why this the carboxylic acid with CH2Cl as a functional group has a higher Ka value than the acetic acid that has a functional group of CH3. Also, there is another vector that determines the acid strength of carboxylic acid, which is electron delocalization. So this is the general equation for carboxylic acid. Okay. In this equation, you can also compare the relative acid strength based on the stability of this anion. Okay. If this anion can be more stabilized for some reason, that means the equilibrium positions will have a tendency to lie a little bit to the right. So So this anion is more stabilized, then equilibrium lie to the right, and the Ka will be a little bit larger. And that's the comparison between these two acids are exact example where you can see the influence of this anion stabilization on the acid strength. So if you compare these two, in case of this, where this functional group is benzene, where, as you know, the benzene has a 공명 구조, the delocalization 구조 structure. So once this H is detached, the anions in this case can become more stabilized, become more stable compared to this CH3, which doesn't have any resonance structure. So the Ka value for this benzoic acid is slightly higher than the Ka value for this acetic acid. Okay. And all the types of acid that we studied so far has a very similar structure where the one proton can be easily detached. So all the acid that we learned has a H in their structure, right? So blah blah H. It can be just HA form. But another types of acid or base that we're gonna study from now on doesn't have any H or OH, which means that even though some materials, some molecules doesn't have any proton, it also can be acid or base. And to understand this concept, what you first need to understand is the hydrolysis by salt, which means the anions or cations. Before we study this page, let's recall that I told you in the beginning of class as an example of CH3 COOH H plus, right? So this is acid. So this acid has a H plus. So it's very easy to tell, okay, this material is acid. And at the same time, this is a base, conjugate base, right? And because this is a conjugate base, you can write down another equations from perspective of this base. Right? And in this case, this acetic acid is a weak acid, so which means that this base can be a little bit strong base because it's as I told you, the strength of acids are opposite to the strength of conjugate base, which means that this reaction actually can happen. Okay, this conjugate base of some weak acid can act as a base to generate OH minus, right? So let's imagine some situations where you have this material. So instead of H plus, you have sodium ions, and this is a very well-known material. And let's imagine that you put these substances into water, and what's the pH of the water? So if you haven't learned anything about acid and base, you are not able to tell because it doesn't have any OH and it doesn't have any H plus. So you can just think that there's no additional formation of H plus or OH minus. But what actually happened is this reaction if you put this material into water. And if you put this material into water, then the pH will be higher than 7 because this acetic acid anion will generate OH minus. This is what you're going to learn for these following few pages. Okay. And let's study from more organized way this concept. Okay. If you look at the title of this page, it tells you hydrolysis by salt. Okay. Okay. Hydrolysis is the ionization of water. So as I just told you, the CH3COO minus will this hydrolyze water molecule to generate OH minus. So this is the one example of hydrolysis. And title is hydrolysis by salts. So salt means some material where the salts can be dissociated into cations and anions. It means that the anions or cations can do some hydrolysis to generate H plus or OH minus. So that's what we're going to learn in this chapter. So every every concept and every problem about strong acid and strong base is very easy. So nothing special is going to happen in case of strong acid. For example, let's suppose that this HA is a strong acid. Then you would expect this almost 100% of HA will be dissociated into H plus and conjugate base A minus, right? And equilibrium tends to lie right. And if this is the case, if this is a strong acid, the strength of this conjugate base is very, very, very small. So it doesn't do anything in water because it comes from, it is a conjugate base of strong acid. So A minus conjugate base from strong acid does not want to receive H plus. So there is nothing going to happen between this anion from weak strong acid. So right. But the situation is a little bit more different and complicated in case of a weak acid. Let's suppose the HA is a weak acid. So in this equation, equilibrium tends to lie left, which means that this A minus as a conjugate base had some measurable strength of base. So this reaction would happen. Okay, this is what I just explained in this slide earlier. This is a conjugate base. Okay, because this is a conjugate base, it can do these equations to generate OH minus from H2O, which is called hydrolysis. Okay. And this same thing can be extended to base, where you can compare the strong base and a weak base. So same with acid. There's nothing special happens in case of strong base. If you put some strong base into water, it just dissociates into 100%, almost 100% of them are dissociated into conjugate acid and OH minus, and nothing further gonna happen. So no reactions from this conjugate acid. But some material is a weak base, which means the B generate OH minus based on this equation. This is a conjugate base, conjugate acid. It has some measurable strength. So if you put this conjugate acid into water, then it will act as an acid, right? To form this H3O plus, which we also call this hydrolysis. So if you, and this conjugate acid in most cases is a cations. So it means that if some salt has cations or anions, which is conjugate base or conjugate acid or of weak base and weak acid, that anions and cations do something further when they dissolved in water, even though they have OH minus or H plus. Okay, and based on this thing, these are the table that you can understand why these examples are neutral and basic and acidic. Okay, in the following slides, I will go through this table step by one by one. So, for example, let's take an example of NaCl, sodium chloride. if you know that this sodium chloride has a sodium cations and chloride anions, and these sodium cations is a conjugate acid of NaOH, right? It's from strong base, and this Cl minus is the conjugate base of this strong acid HCl, right? And as we know from these two pages, the cations and anions from strong acid and strong base, they doesn't do anything special. So if you dissolve NaCl into water to generate Na plus and Cl minus, nothing gonna happen. So NaCl solution with NaCl has the pH of 7. And same thing can be applied to other salts such as Ki and KNO3. And you can tell for this, for example, this Ki, KOH is a strong base and HI is a strong acid. So both cations and anions from strong acid and strong base. So nothing gonna happen. Same thing for KNO3, right? KOH, strong base, and HNO3, just strong acid. So both anions and cations are from strong acid and strong base. So nothing further gonna happen. Okay. But if I repeat, in case of the CH3COO-Na, Na plus cations, Na plus is from strong base. So Na plus doesn't do anything. But CH3COO minus anions is from weak acid. So that this is gonna do something further, which is hydrolysis of water to generate OH minus. So the solutions that contains this CH3COO-Na has a pH higher than 7 to become basic, because this acetic acid anion from weak acid, it makes hydrolysis happen to generate OH minus. So even though this salt doesn't have any H plus and OH minus, the solution that has this salt can become acidic or basic. And the same thing for KNO2, right? KOH, K plus, KOH, strong base. So K plus doesn't do anything, but NO2 minus is from HNO2, and you know HNO2 is a weak acid. Don't be confused with HNO3. HNO2 is a weak acid. So NO2 do something in the same way as this to generate OH minus. So KNO2 solution with KNO2 becomes also a basic. Okay. And you can do the same thing for these. For example, let's take an example of this NH4 plus. NH4 plus is the conjugate acid of a weak base, NH3, right? So it does something. Right, to generate HNO3 in water. However, the Cl minus here, the anions, Cl minus is from HCl, right? So it doesn't do anything. So the solution that has NH4Cl becomes acidic to have a pH lower than 7. Okay. Then what if the both anions and cations comes from weak acid and weak base? Then the situation is based on their relative Ka and Kb. For example, let's look at this example. This example, it has a NH4 plus and it also has a NO2 minus, and they both from this NH4 plus comes from a weak base NH3, and this NO2 minus comes from weak acid HNO2. So they both can do hydrolysis right? And at the same time, because they are conjugate acid and conjugate base, from the table you can find the Kb and Ka for these anions, cations. So this is an acid, so this would have a Ka. This is a base, so this would have a Kb. So if here the Ka is larger than Kb, then there is more H3O plus generated, right, than OH minus. Then there is more H3, so solution becomes more acidic if the Ka is larger than Kb. And if they are about the same, Ka and Kb are about the same, then the pH going to be just 7, around 7, neutral. And if the Kb is larger than Ka, there is more OH minus going to be generated, then the solution is going to be basic with Pa larger than 7. Okay. And the last example is that this is the special example where the small and highly charged metal cations such as aluminum 3 plus, iron 3 plus, chrome 3 plus, bismuth 3 plus, all these small and large high oxidation state metal cations, they just can react to water to generate H3O plus. So for example, based on these schematics, the highly charged cations can attract OH minus from water, leaving H3O plus behind to make solution acidic. So in this table, for example, this aluminum chloride, Cl minus is from HCl, right? So it doesn't do anything because it's from the strong acid. But aluminum 3 plus, it will generate H plus because it's a highly charged metal cations. So the solutions will become more acidic. We will become a little bit acidic with pH less than 7. So this table is called the acid-base properties of salt, cations and anions. So this is very important. So why some salt is acidic and why some salts are basic, depending on where the cations and anions came from, the weak acid, weak base, or strong acid or strong base. And you should understand their relative relationship based on their relative strength of acid and base. Okay. So next time, next lecture, I will review this table because this table is very important to understand. And after next time class, we have a two times 휴강 for 추석 holiday. So depending on the progress of our lecture, because we have to finish the chapter 16 before we do midterm. So depending on the research lecture progress, I will upload the recorded online class during the 추석 week. So, okay, and see you next time.